All right, let's get started. Problem set number 5, I think, is about to be posted on BSpace, and instead of 11 a.m., so you can get an extra 3 hours of sleep, we do at 2 p.m. Next Wednesday. Reading, finish up 12.1, 43 pages 431 and to 434, and also posted on the wiki this morning is the reading for next week. That's chapter 24.1, and then a couple of odd pages throughout that chapter, 881 to 886 and 920 to 922. So read that for next week. Is everyone going on to BSpace fairly regularly and checking out the wiki and things? Okay, good. So you're in tune with that. I realized that last week I didn't tell you the reading in class, but it was there on the wiki. The colloquium today is going to be given by Aaron Parsons, who's a postdoc in the department here, and he'll be talking about 21 centimeter emission and absorption at high redshift. So you've seen a bunch of these words before. We'll be talking about 21 centimeter emission and absorption today, as luck would have it. And high redshift is something that I've mentioned before in a cosmological sense. Basically looking for the signatures of gas in the very distant reaches of the universe. So that's at 4 p.m. today in number 1 LeConte. I suggest you all go. And one of the things I wanted to mention, because I know a number of you are thinking about doing research or maybe already engaged in research, is that one way to sort of at least get a pulse of what's happening, not so much at the press release level, which can be fairly biased towards like exoplanets or things that are fantastical but are completely wrong, is to look at the papers that people are actually writing on a daily basis. And we post this to what's called the preprint server. The URL is archive.org. And you can actually sign up to get email listings of all the abstracts of the papers that have been posted for the day. Here's this morning's set of abstracts. And it's kind of neat to go through, I think, and even just reading the titles and getting a sense of the things that may excite you for your own future research, and also helps you sort of reconnect to some of the topics that we've discussed here in 7b and in 7a. In particular, let's see, we talked about gravitational wave emission already, right? So you go, I know what that means, sort of. Anyway, so I want to make sure that you're all sort of in tune with this, and I realize that I've been telling you to go to these various colloquia, or suggesting that you go. You don't have to go. But this is just sort of another way to do that. You can do that on your own time. Any questions about logistics? Okay. So last time we talked about dust in the interstellar medium. And there are some important features of dust. Namely, what? How does dust manifest itself? Reddening. Reddening and what? Extinction. It also, as part of the extinction, we said had this 2175 angstrom bump, as it's called, which is an extra bit of extinction over what you'd expect from the extrapolation from lower and higher wavelengths. And we think this is due to some carbonate of size something like 200 angstroms. The other thing I mentioned, but just want to make sure that you had in your notes, is that there's a temperature associated with dust. And that's something of order, of course it depends exactly on the nature of what's heating the dust, something of order 20 Kelvin. So you can look at a cloud in our own galaxy that is thought to have dust and is already, as you can see, absorbing starlight behind it, because that starlight is reddened and extinguished. And you can actually, if you go to long enough wavelengths, you can actually see the black body emission from the dust itself. It's not purely black body because there are some certain features in the dust. In particular, here's one of them. There's another feature like at 10 microns due to silicate. But the point is that if you're absorbing all of this energy, or a fraction of the energy that's coming into this gas cloud, it's going to have to wind up getting radiated, and that gets radiated more or less as a black body. Okay. We also saw last time that the extinction at the visual wavelengths, so around sort of 5,000 angstroms, let's say, was proportional to the optical depth at the visual wavelengths. And remember, the optical depth is going to wind up being proportional to this thing that we called lambda. But in this case, lambda would be something like 5,000 angstroms if we're looking at the visual wave bands. So one way to think about how extinction should go in this Mie theory, this Mie scattering theory, where the wavelength of the incoming light is about the wavelength, or about the size, typical size of the grain. Is that this has to be proportional to some sort of sigma divided by lambda. And likewise, this tau as a function of wavelength is also going to go inversely with lambda. Right? Remember what we said is that this this sigma is going to wind up as a function of lambda is going to be something like sigma of the grain divided by lambda times some constant, right? That's from this Mie theory regime. So this is something that you've already seen in the schematic that I drew for you on Tuesday, but it's also in your book, where you can see that there's this overall dependence where the extinction is basically going down as lambda. So if I was going to draw this a lambda and now the logarithmic of lambda, this would be basically a straight line through the optical regime. And then, of course, we have this extra little bump and things like that. But for the most part, this should help you remember that as you go to longer wavelength, extinction is going down. And you all remember what this A term is, of course. That's just the extinction term. Any questions about that? This is sort of already in your notes in various places. I just sort of wanted to tie it all together so that you had it in place. Yes?
So why do longer wavelengths pass through dust?
Well, I mean, the sort of hand-wavy answer is that when you have a incoming photon, it's got a wavelength associated with it. It's going to be interacting with the electrons that are part of whatever it's hitting, right? And if the sort of distribution of those electrons is on the same typical scale, then the interaction can be pretty strong. If it's not, so the thing is actually a much higher wavelength, it could actually pass through the atom. This is why an X-ray photon is quite happy just essentially passing through a hydrogen atom. Likewise, a radio photon is very happy passing through a hydrogen atom because the wavelength is so long, it's not interacting on the sort of typical scales that the electrons want to interact. So the hand-wavy answer is that at the atomic level, or even the quantum mechanical level, you have to be interacting on the scales that the electrons are distributed. And since the electrons are going to wind up being distributed, assuming this grain isn't very ionized, they're going to be distributed within the sort of clouds that make up the bonds between the different atoms in this very large molecule. And those have to be of sort of this typical size. So the interaction's reasonably strong. Why it goes down like 1 over lambda, I can't give you a sort of very good reason for that. Because remember, we said that in a different regime, it can go down very strongly as 1 over lambda to the 4th power. There's a whole theory associated with getting this 1 over lambda. It's a good question. Yes?
Shouldn't it not just go down then? Shouldn't it go up at first?
Yeah, so this is sort of the ultraviolet, optical, infrared picture of extinction. As you wind up going to so higher frequencies farther and farther down, what you notice is extinctions go up, but then all of a sudden it basically just drops off like a rock. And it's because basically all of a sudden the photons stop seeing those electrons, right? And when you get to very, 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 very high energies, then you start getting to sort of nuclear scales, and then you can actually wind up interacting with the nucleus, right? But that's at sort of TeV energies. But yes, as you go farther and farther down, basically your extinction is going to more or less go like this. Does that answer your question? Okay. Yeah. So this is sort of a little bit of a biased view in the electromagnetic part of the spectrum, where people are sort of always making measurements of dust. There's interesting things, of course, that an ultraviolet photon, which does actually get absorbed by a dust grain, could rip a couple of the electrons off of that dust grain, and then all of a sudden this dust grain is charged. The dust grain gets charged enough, it could actually wind up ripping itself apart because of the Coulomb interactions of the various electrons. So if you throw a lot of UV photons at dust grains, you can actually destroy those grains. Yes?
Why is it plotted against log lambda?
It's just so I could draw it as a straight line and not as a curvy line.
Wouldn't it be less than 0? I mean, wouldn't it be negative then, since lambda is less than...
What do you mean?
Wait, never mind, that's
So-
ln, I think. Never mind.
I mean, it's going to basically be going down. You're saying that it's going to have some slope. It's going to have some intercept here.
No, yeah, I think I got it confused.
Okay. All right. That's just for convenience of me plotting. Okay. Any questions about dust before we move on to other stuff? Right. So interstellar gas. Actually, an important constituent of the Milky Way makes up something like 10 to 20% of that of the stellar mass in the Milky Way. So if you took all the gas that's actually associated with stars, the stuff that makes up stars, and you weighed that, and then you weighed all the stuff that isn't associated with stars, that is just sort of this diffuse interstellar stuff, then you would get something like 10 to 20% of that interstellar stuff in mass relative to the stuff in stars. That's actually fairly low. As you go to larger distances away from us, so earlier on in the universe, it looks like many galaxies were more gas-rich, right? Because these stars all had to come from somewhere. They had to come from gas, right? So over time, the sort of some of the forward march of time tells us that we're going to be using more and more of our gas as we go on. And in fact, when you look at very old galaxies that don't have much gas at all, this fraction can be much, much lower than the stellar mass, because more or less you're just using up that gas over time. We'll see more of that stuff later on. It exists in various states. The sort of coldest state, as you might think of it in terms of temperature, is molecular. Next might be neutral and atomic. And the last might be ionized. This is sort of a sense of cold to hot. Why might that be? Well, the bonds that hold, say, two hydrogen atoms together are giving us something called H2, are much easier to break, or much easier, are easy to break relative to the energies required to take a neutral atom and ionize it. So sometimes we call neutral hydrogen H capital I, or H1. And one of the very confusing things when people are just talking in the elevator about the interstellar medium is when they're talking about H2 or H2. So unfortunately, this is something they have to clarify when somebody says H2. Yes.
I often see that as a subscript as well. Is that common? With
The little, it's not very common with hydrogen. You often will see it with other elements, but with hydrogen, this II is promoted to the same capitalization. Anyway, so this is a neutral hydrogen that could be in an excited state. Doesn't have to necessarily be in the ground state. This is hydrogen that's had its electron liberated from it. They exist not just in a sense of temperature, because each one of these atoms is going to be moving with some characteristic velocity. That characteristic velocity is going to be associated with an overall temperature of that gas. But they're going to also exist at different pressures and densities. And we'll see some of these numbers later on. So the big picture in understanding the distribution of gas in the Milky Way, of course, is that we obviously want to understand where a large fraction of the baryonic mass is of the universe, and a great way to do that within our own galaxy. We'll see probably late next week that we can use H1 in particular to help us make measurements of the overall structure of the Milky Way by looking at spiral arms, and in particular looking at the typical velocities of how the material in the spiral arms are moving. And that gives us an overall way to make measurements of the mass of the Milky Way. But the big picture today is the idea that if we want to understand where stars are formed, we have to understand these different states. We have to understand how we make measurements of the gas in these very different states. And to get a sense of star formation, we must understand how this gas is distributed in this temperature, pressure, and density. And in particular, in a more quantified way, we have to understand whether gas clouds are satisfying the Jeans criterion. Can somebody who took 7A give me sort of a summary of what the Jeans criteria is and where it comes from?
It's how much gravitational potential there has to be in a gas cloud before it'll start falling in on itself and collapsing into a star.
Right, good. So that's a good summary of it. How do we start off in the derivation of the Jeans criteria? Not really. We're not talking about a pressure structure throughout the gas cloud.
You have to balance the gravitational energy with the, is it the thermal energy?
Yeah, that's right. So in doing that, you would imagine that a gas cloud in thermal equilibrium, all the particles are basically happily obeying virial theorem, right? And if I want to have the gas cloud collapse on itself, the total energy of the cloud has to be negative. If it's positive, then it winds up expanding out. If it's negative, it winds up contracting. And so if you go through this exercise, and those that weren't in 7A, I encourage you just to look back at chapter 12.2 in Carolyn Osley. We won't test you on this per se, but this is just to give us some context of the relevant quantities for star formation. If you want to actually solve that equation, you basically set energy equal to 0. You use the virial theorem, and you wind up solving for a mass in terms of density and temperature. That mass, called mj, is 5 kT divided by g mu mh to the 3/2 power, 4 pi rho of the cloud as it is initially, divided by 3 to the minus 1/2 power. T is the temperature of the gas, rho is density, mu is this thing called mean molecular weight. I'm kind of introducing this criteria now. We're going to wind up using it again in the context of galaxy formation, so it's helpful to just have seen this at least once. What mean molecular weight is basically the average mass per particle in dimensionless units, basically in units of the mass of a proton. So the mean molecular weight of neutral hydrogen Why? Who said 1? Why'd you say 1? Yeah. Yeah, it's an easy one. So let's see, mean molecular weight of H2, H little 2. Average mass per particle, yeah, 2. Mean molecular weight of ionized hydrogen, 1/2. Yeah. Anyway, so you can plug in these numbers once we see what the temperatures are and the densities are of these various clouds, and you can see whether this cloud satisfies the Jeans criteria. That is, if the cloud is larger than this Jeans mass, then portions of it are capable of actually collapsing. Right, so we have to understand what these temperatures and densities are. All right, so let's talk about detecting gas in the interstellar medium. We'll focus on hydrogen and a couple other atoms and a couple other molecules, but it's sort of fairly generic. Hydrogen is the most abundant element in the Milky Way and in the universe, so it makes sense to think about how we might detect that. Well, there's really two ways of doing this. One is through absorption, and the other is through emission. Let me focus on absorption for now. Let's say I have this bright star, and it's putting out lots of photons, and I detect the spectrum of that star, and then I put a cloud in front of it. Let's forget about dust for a second. We know that the dust would wind up extinguishing the light and making that light appear more red. If that cloud had gas in it, if it had some atoms, it had some molecules, etc., what would be the fingerprints of that gas on what it is that we would wind up detecting? There would be some narrow absorption lines, right? So if I just had a pure ball of hydrogen, there are specific transitions where if I have a photon coming in at exactly the right wavelength, it will get absorbed. And if, let's say, that hydrogen atom is in its ground state, if it has exactly, say, 12, 16 angstroms, it will go from the ground state up to the first excited state. That's called the Lyman alpha photon. So that means that if I wind up absorbing that Lyman alpha photon, that photon which would have otherwise gotten to me is now gone from my spectrum. And so if I have a conglomeration of all of this hydrogen, then I wind up more or less absorbing it. So what I wind up seeing, here's my star. Here's my cloud. Here's me looking at that star through this cloud. We can just call it basically neutral hydrogen for now. I wind up seeing a spectrum that has some notches in it. And these notches, this is a function of wavelength or frequency if you'd like, these notches are going to have certain rest wavelengths that we'll be able to identify because we'll see a number of different notches. So we'll say, that looks like the Lyman alpha transition of hydrogen. And there I go, right? All of a sudden I know, well, now I can sort of do the math and figure out how many photons are missing from this spectrum. And then I can figure out sort of what the column density of hydrogen is through that cloud, because I can infer the optical depth. There's a problem with this, though. Yes, Pauline?
Yeah, wouldn't the star have neutral hydrogen in its atmosphere?
Well, maybe not neutral hydrogen, but it could certainly have excited hydrogen, right? It depends on the temperature of the star. But you're absolutely right. This is a significant problem. There's a way to get around this, Anthony.
When they look at the spectra, I think it's along the same lines as you get to it. But when you look at the spectra, how do they know it's just not, that's what the star is?
Okay, good.
You know?
Well, let's think about, so let's say that the star has a temperature that would allow this transition to exist in the atmosphere of the star, right? Because the way that you get absorption is that you have some bright emitting source, and then you have some dark source at certain wavelengths in front of it. That's what absorption looks like. Well, let's think about it. How might we distinguish this from an absorption line in the star itself?
Well, we'd have to have an absorption that didn't happen in the star.
You could do that too, but I want to actually take one of these difficult cases where it's an absorption line that actually exists in stars and also in the gas that I want to study. Leah?
Isn't there something to do with how skinny or how wide the lines are?
Yep, that's one of the ways. So explain that to me.
Well, I know that stars that have a continuous spectrum, they don't actually necessarily create the continuous spectrum, but it's just that while photons are trying to escape the star, they bump into other things and become the continuous spectrum, so things get kind of shifted. Correct me if I'm wrong.
You're getting there. I mean, so there is this overall temperature which is associated with, if you want to think about the emission and absorption structure of a star, think about this whole thing at some temperature with some black body temperature associated with it, and then think of all this stuff as optically thin. When you observe this, you see a black body spectrum but notched out by these different lines here.
But even the gas that's on the outside is still going to be pretty hot and it's still going to be moving pretty fast.
Okay, so how does moving gas manifest itself in an absorption line? Broadening, Doppler broadening, exactly. So when you have a reasonably hot gas, all these different atoms are moving in various different directions, and the faster that they're moving in a given direction, for a photon that's coming into them, they're only going to be happy to absorb that line at what appears to them to be one of these exact atomic transitions, right? If it's moving fast away from a photon which is coming towards it, it sees that photon redshifted or blue shifted. It sees that photon redshifted, right? So it's going to be happy absorbing at a longer wavelength as viewed by us, right? And likewise, an atom which is moving towards an incoming photon is going to wind up doing the absorption on the blue side of this. But on average, it's going to wind up the majority of the absorption is going to happen at the sort of zero wavelength of this transition. Another way to put it is if you associate some width with this absorption line, delta lambda divided by lambda looks like kind of a redshift, right? So you can imagine this has got to be something of order v divided by c. We know that v, if we just want to play a game of 1/2 mv squared is equal to 3/2 kt. Doesn't matter what the numbers are out here. This says that v is going to go something like square root of t divided by m. I can put this in here. So this is Doppler broadening, as someone mentioned. And one of the things I can see is that in interstellar absorption clouds, these line widths, delta lambda, are small, requiring very low temperatures. Certainly less than 200 Kelvin, but probably in many cases more like 100 Kelvin. That does not look like the atmosphere of a star, right? So one of the ways to do this, to distinguish whether you're getting interstellar absorption or whether you're getting absorption from the atmosphere of the star, is by looking at the characteristic width of these lines. What's another one? This is actually the easier one. Yeah, I want to just do absorption now. But yeah, emitting also makes it easy too. Yes?
Do you know where the photons might be, and you also know that the star is moving if you look at the Doppler shift of the whole line?
Of the whole pattern of lines. Yep, exactly. So say I just had a very simple spectrum of a star, which was a black body superimposed with a bunch of absorption lines due to hydrogen, right? There would be a characteristic fingerprint of all these different lines. There would be a velocity associated with that fingerprint. And those would have very sort of wide line. Those would be very wide absorption lines. And then if I wind up going through an H1 cloud, it's going to have a different apparent velocity relative to us, right? Because there's going to be a redshift and blueshift effect, because stars are not all moving exactly along with us. And so if I look at a random star, there's going to be some redshift or blueshift of order sometimes 50 to 100, maybe even 200 kilometers a second. If I look at a nearby gas cloud, it's going to have a different velocity relative to me, which is also the same way as saying that the photons that are coming in here are seeing basically a different velocity of that background star. So you actually can wind up getting, if you allow me to draw this here, some broad absorption line from the star, and then a narrow absorption line from the same transition from the gas cloud. That's from the star. That's from the ISM. And we're not just going to go through one cloud. We may go through several clouds, right? And they'll have different amounts of hydrogen in them, and maybe at slightly different temperatures. So you actually can wind up seeing sort of very complex absorption structure. Just to give a couple of wavelengths of interest here. If I just draw a neutral hydrogen atom and the bottom three energy states, n equals 1 to 3, if I wind up absorbing a photon that takes us from the 1 to 2 state, this is called Lyman alpha. And the photon, as viewed by the atom, wants to be 1216 angstroms. If I now have an electron in this first excited state and another photon comes in, and it has, as viewed by this atom, a wavelength associated with this transition called H alpha. This is 6563 angstroms. If I have a hydrogen atom in the ground state, and I want to ionize that hydrogen atom, this is called the Lyman limit. That's 912 angstroms. Nine 12 angstroms in electron volts. Does anyone remember what a Rydberg is? 13.6 eV. Yep. So this is hydrogen. Obviously, if I have more complicated atoms, I could have many more transitions. These are sort of the very, very important transitions for hydrogen that you need to know about. Right. Turns out, if I have a Lyman limit, I have a photon that comes in at 912 angstroms. I take a a hydrogen atom in its ground state and I ionize it? What if I have a photon that comes in at 9, 10 angstroms? Doesn't or does? Yeah, so it's not a discrete transition anymore. It's a continuum transition. As long as I have enough energy above 13.6 eV, then you get into weird things when you get into the X-ray regime, right, where you have to deal with the fact that the wavelength of the photon is so small. Then I have a continuum of absorption. So if I'm just epsilon smaller in wavelength or epsilon higher in energy, I also will ionize that hydrogen atom. So what you wind up seeing in a spectrum, so this is F nu and this is lambda increasing in the right, is that I would see this spectrum and then all of a sudden it just drops off at 912 angstroms. Basically, if you have gas of just neutral hydrogen, it's more or less at the ultraviolet, these are ultraviolet wavebands, it's more or less opaque at ultraviolet wavebands. This is pretty far down into the ultraviolet. It's not actually something that we can see on Earth because the Earth's atmosphere is actually much more opaque, starting at around 3,000 angstroms. But unlike this absorption, say, at 12, 16 angstroms, which is a discrete transition, we wind up having a continuous transition, blueward of 9, 12 angstroms. Okay? Yes?
So how do we ever see? Oh, never mind. Sorry, I had a decimal place in the wrong place.
Okay. Right. The other thing to note, of course, is that if I have my dust cloud, if I have a cloud, it could have both dust and neutral hydrogen in it. And the dust itself may actually have hydrogen in it, right? So just by sort of doing all the math to figure out what my optical depth is, to figure out what my column density is, to figure out what my temperatures are, blah, 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 I don't necessarily get a full accounting of all the hydrogen because some of that hydrogen is already tied up in molecules, which won't give us these very sharp transitions, right? It's only from atoms in the gas phase that we will get this. Okay. So that's hydrogen in a cloud in absorption. What I want to now focus on is detecting hydrogen in emission. Were there any questions before I moved on? Yes?
Why do you keep plotting F nu by lambda? Does that make sense?
I can do whatever I want to do. It is a little bit schizophrenic, but this is actually how most astronomers will plot a spectrum. We think, for some reason, in units of F nu, just historically, but it's kind of nice also to look at wavelength increasing to the right. But I could just as easily do this and have frequency go to the left. It's the same thing, right? Does that make you happier? Okay, yeah. But good, it's a reasonable question. All right. Let's talk about neutral hydrogen in emission. Neutral hydrogen in its ground state, you would think couldn't do any emission, right? But it turns out that it can. And this is called 21 centimeter emission. From neutral hydrogen in the ground state. And this is actually a fairly powerful tool for us to study the distribution of neutral gas. And the way to think about this transition is that electrons and protons have spin, even though this electron might be sitting in the ground state of this hydrogen atom that is bound to the proton. There's going to be a spin associated with this electron and the proton. When you have this spin, effectively you're going to wind up having a magnetic field. There's going to be an energy associated with that. And there's an energy associated with this configuration where the spins are aligned. There's another energy associated with the spins being anti-aligned. And if you think about this for a second and think about sort of taking, a magnet with a north and a south and a magnet with a north and a south, is this in a state that's fairly happy, or does this state want to spin around and change itself? It wants to spin around. This is a higher energy state. It wants to get to a lower energy state where the south is touching the north and the south. And the exact same thing is happening with hydrogen atoms in the ground state. This is a higher energy state, which you could have figured out because I drew it higher on the board. This is a lower energy state. This is actually the true ground state of hydrogen. And this is a very small difference in energy, which corresponds to a wavelength of an emitted photon as you go from this state down to this state of 21 centimeters. And that's 1,420 hertz. No, megahertz. Megahertz, yeah. Decidedly in the radio regime. The lifetime, once I get myself into this, by the way, how would I go from being in this very, very low ground state of hydrogen to an excited state? What's that? Yep. What wavelength of light would I have to absorb to get that? 21 centimeters. What if I don't want it? What if I don't have an illuminating source that's very bright at 21 centimeters? Collisions, yes. Collisions of what to what? Yep, that's right. So hydrogen, just a ball of pure hydrogen that's interacting with other hydrogen atoms, the collision rate is very, very low, but it's high enough that you can actually bump a hydrogen atom with another hydrogen atom, transfer a little bit of energy, and sort of push them both up into this semi-excited state, not one of the electronic states, but one of these fine states. Yeah.
Why does the spin create magnetic?
Well, it's charged, so spinning. Yeah, but there's a magnetic dipole moment. There's a magnetic dipole associated with the electron and the proton, right? And there's going to be there's a vector associated with that dipole. It's either up or down. You can think about it as the dipole up or down, or you can think about it as the spin. Yes, Anthony.
Why does that be in the ground state? Can it be in the first excited state and flip?
It could. It just turns out that the amount of time that you spend in the first excited state before spontaneously dropping back down is much, much lower than the time that you spend in this higher state, in the ground state. So there's no time really spent there. There are these very, very fine differences in these excited states, but they're not very important for what we can observe. No, because it's going to wind up being some quantum mechanical difference at that higher energy state.
So are all magnetism in general just what this is?
Just alignment of spins of electrons?
Yes. So is it all spin or?
Yes. Thereabouts. I'm sure there are different ways to conceptualize it, but yeah, when you have an ordered lattice of material, like you take some diatomic material, you have all the atoms which are sort of co-aligned along these. You wind up having the atoms that are co-aligned such that the spins are all sort of pointing in about the same direction. And so they all sort of add up, and that's how you wind up getting your sort of macroscopic magnetic field. The total time that's spent in this transition on average is 3 times 10 to the 6 years. So you take a hydrogen atom, you bump it a little bit, give it a tiny bit of energy. It's going to stay in this state very, very happily for a long time until it spontaneously winds up decaying. 3 times 10 to the 6 years, how many seconds is that? How many seconds are there in a year?
3 times 10 to the
Yep, 3 times 10 to the 7. Yep, 10 to the 14 seconds. That means I need something like, for every 10 to the 14 hydrogen atoms, it means I get 1 21 centimeter photon per second. It's a good thing that there's a lot of hydrogen in the universe. And what's interesting is that you can actually create an optical depth to either absorption or emission. In this case, this would be an absorption. And this is 5.2 times 10 to the minus 23 NH in units of centimeter squared times the temperature in units of Kelvin times the velocity of the gas in units of centimeters per second. So I get an optical depth of 1 for sort of typical numbers here. I have to have a tremendous column density of hydrogen. Remember what we said about NH is just the integral of little NHI ds through the cloud. Column density. All right, let's take a look at that. This is not our galaxy, but another galaxy. On the right, what you see is a typical optical image of galaxy M33, nearby a bright galaxy. You see the blue stars. You see some effects of dust because you have a lot of absorption. These stars appear redder here. You see some dust lanes in those galaxies. And what you see on the left-hand side is a 21 centimeter image of that same galaxy. And it's color-coded because this is basically hydrogen in emission, but the galaxy is rotating, so there's an overall Doppler effect. This part of the galaxy is moving away from us. That part is moving towards us, so there's a blue shift, red shift effect. So the detection of this 21 centimeter light is not exactly at 21 centimeters, but a little bit longer wavelength and a little bit shorter wavelength. And you can see some of the same structures persist, so you can still make out some of the same spiral arms. This is on the same scale. But you notice, like in here, there's not a whole lot of stars. Probably these are all background galaxies or foreground stars in our own galaxy. There's not a lot of gas there. But what you also notice is that far out here, where you don't detect any of the optical light from stars, there's a tremendous amount of gas. So in fact, in our own galaxy, beyond where we think the sort of typical size of the galaxy is in terms of where the stars are, out to factors of a few beyond, there's plenty of H1 gas out there that we can detect at 21 centimeter. Now, it turns out that as we get to very cold temperatures, there tends not to be a lot of neutral hydrogen, but hydrogen likes to get itself into an atomic state. And there's no 21 centimeter emission from hydrogen H2 in the atomic state. So we have to detect the gas in a different way. When it's cold, we expect molecules. And from molecules, we can expect both absorption and emission. Way to think about a molecule, call it a carbon and oxygen molecule, is that you basically have two atoms that have some mass 1 and mass 2 associated with them, and they are spinning about their center of mass. Think of this more or less as just a dipole, right? think about the rotation of this, and in particular moment of inertia, symbolized by a capital I, and this is just m1 times r1 squared plus m2 plus r2 squared, where the difference from the center of mass of the carbon atom to the center of mass of the whole system is r1, and this is r2. The interesting thing about this is that it's not that I can just sort of flick this oxygen atom and it winds up spinning around at whatever rate it wants to spin at. At the molecular level, these spins are going to wind up being quantized quantum mechanically. That is to say that the angular momentum is quantized. From quantum mechanics, I times omega, the spin frequency of this molecule, is what we'll call the angular momentum of the system. This is not something that I would expect you to have to know, but just sort of refreshing your memory for those that have taken some quantum. This is j plus 1. So this angular momentum, the sort of magnitude of the angular momentum is Planck's constant divided by 2 pi times the quantity square root of j times j plus 1, where j is just a number, 0, 1, 2, 3, etc. The total energy, rotational energy level, that's associated with this spin is just 1/2 I omega squared. Looks a lot like 1/2 mv squared. Think of I as sort of a rotational mass and omega as some sort of rotational velocity. If I multiply this by I and I divide it by I can get an I squared over here. This winds up simplifying to 1/2 L squared divided by I, which is H squared divided by 8 pi squared j plus 1 divided by I. I'm not really carrying through the derivation here for you. I'm just sort of showing you the final results. If you put in the value of I here that we can wind up calculating, because I know the mass of a carbon atom and I know the mass of an oxygen atom, you wind up getting an energy associated with that. If I associate that energy with a frequency, then I wind up seeing that the absorption and emission of CO is in the millimeter regime. So if I have a millimeter detector, which looks a lot like a radio receiver, then I can detect the presence of CO. And the point is, I can detect the presence of CO in a very, very cold cloud. Now, it turns out you can also detect the presence of H2, that is little h2, or big H, little 2, molecular hydrogen, through its absorption at ultraviolet wavelengths. But it doesn't radiate very strongly, for reasons I won't have time to go into, at these wave bands, or much at all, actually. So it's actually very difficult to detect H2. One of the things that's fairly interesting, however, well, let's take a look at the CO map of our galaxy. This is somewhat complicated, but this is a very classic map, so I thought I would show it to you. All right, so first of all, you can't see this, but you'll definitely see it when I post the notes. This is L equals 0, where L is the galactic longitude. Right? We've already thought about longitude and latitude. We thought about it in different coordinate systems. Now I'm going to do it in galactic coordinate systems. And towards L equals 0, I have the galactic center. And as I go farther out, I wind up wrapping all around. So think about sort of taking this here and wrapping it around you and getting the full picture. And if you're staring in this direction, you're looking towards the galactic center. The up and down direction is velocity, right? So if I know a transition of CO that I'm looking at, it's not going to be exactly at its rest transition. Some of it will be moving towards me, and some of it will be moving away from me. This is a positive direction, so this is redshift. This is a negative direction, so this is blue shift. The overall galaxy is rotating, and we can see this manifest by looking at the CO clouds. And as you see, as I get towards the center, I have very, very large velocities, both moving towards me and away from me. As I go farther around, I wind up noticing that it sort of has this overall structure around me. If I get to this part right here, which is the same as this part right here, I'm looking out of the galaxy along the galactic plane. And what you wind up noticing is there's not a lot of CO clouds. There's not a lot of dense CO clouds there. The color coding here is the intensity of that emission, so that's how much stuff you actually have. You could think about this as an optical depth or some sort of emission measure. And the redder you wind up getting, the more of that stuff there is. So this is within the spiral arms. This stuff is also within the spiral arms. Were there any questions about that? One of the things that I wanted to show you is that this CO map, which is what I showed you before, now not in velocity space, but now L, galactic longitude, and B, galactic latitude, going only 1 degree above and below the plane. This is this distribution of CO. And what you see up here is a distribution of dust inferred from emission. You can see by eye that the dust and the CO correlate with each other, right? They're actually quite correlated with each other. And this is another dust map that was made at lower resolution, and it's also sort of consistent with what you see up top there. This is pretty interesting and pretty useful. Whenever you have dust, you also probably have some amount of molecular CO. And CO, as it turns out, is a very good tracer of molecular hydrogen. Oh, by the way, people are trying to figure out what that exact tracer is, and on AstroPH today there was a paper called the CO to H2 conversion factor from infrared dust emission. So tying all those things together that I just mentioned. How is it that we get into a different state, rotational energy state? If I have a CO atom or CO molecule and it's just sort of spinning along at some energy state, how would I go to a higher energy state? Crack? Crash. Yeah, collisions. Yep. So collisions will also take us to a higher energy state. And likewise, there's a probability of transition. The number density, so capital N CO divided by NH2, little 2, is something like 10 to the minus 4. So for every 10,000 molecular hydrogen atoms, I have one CO molecule. It just turns out that those are easy to see. What do you think the rotational energy states are of C12O2 versus some isotope of carbon? Are they going to be exactly the same? No? No, right. And why not? Yep. By just a little bit, right? Only fractionally, but enough that you shift the whole spectrum. And what's interesting, of course, is that means that if you know what fingerprint you're looking at, what line fingerprint you're looking at, you can actually start figuring out isotope abundances of various elements in these various clouds, which helps you understand the process of star formation, because then you see where all these different isotopes came from. The way to sort of visualize the existence of molecular clouds is that you have this H2 region, which is cold. Around it, you have H1. And here you could have some UV source that's trying to get at this cold cloud. So maybe you have a very bright O star here. This O star winds up putting out a lot of UV photons. And it could actually, on the outskirts here, ionize a thin layer here. But as it winds up going through, you spend all this energy from the O star ionizing neutral, otherwise neutral hydrogen, and it winds up getting through into here, but you don't have enough photons to do any significant ionizing anymore. The things that get through are the longer wavelength photons, and there you just wind up having hydrogen in an excited state. But what you wind up doing is you wind up protecting this molecular hydrogen. So this is warm, and this might be considered hot. So H1 in the Milky Way shields H2, little h2. By the way, there aren't just these rotational states. There's also a vibrational state. And the way to think about it there is not some sort of spin, but think about a spring between C and O. And you can wind up getting into quantized spin and rotation. These are called rotovibrational states. And yes?
I'm actually still, or maybe it's something better to talk about us, but I'm still confused as to like why you could use CO as a tracer for like.
So inside of here, there's also CO, right? As I go farther out, there's much less CO because it's quite easy to disassociate. It's called photodissociation. It's quite easy to take a ultraviolet photon and hit this CO molecule and have it photodissociate. So where you get H2, you also get CO, you also get, in some cases, water. You can get lots of molecules that survive, but it has to be very cold. Okay, so there are also vibrational states. Which give both rise to emission and absorption. Okay, so that's how we would detect basically molecular clouds in emission. There's also ways in which we can use other emission processes to help us detect the presence of gas in the interstellar medium. And I've started to hint at that by giving you this picture over there on the left-hand side. There is a process called fluorescence. And this is when you have a cascade of transitions to lower and lower energy states. So if I have a hydrogen atom, actually if I just have a proton, which is not bound to an electron, because electrons are all flying around, so I have some ionized gas. So this is an H2 region, as it's called. And you wind up capturing this electron, so you wind up getting the electron to a very sort of tenuous bound state. What you notice is that the electron winds up sort of cascading down levels till it reaches back down to the ground level. And in that cascade, each time it winds up dropping down, there's a probability of transition from each of these different levels. It doesn't have to go down to the next one below it. It could drop down a whole lot. And in fact, the way in which you might get Lyman alpha emission is if you had a whole bunch of material which was in the second excited state, n equals 2, down to n equals 1. Had it get there from an ionized state, it may have dropped from this ionized state all the way down here. You can see that if I'm in a unbound state, so beyond n equals infinity, right? So I'm unbound to this proton, and I wind up dropping down into one of these bound states. There's a continuum of what that can be, because I can have an electron with any amount of energy that I want. And dropping back down into this state means I get this sort of continuum. But once I'm in one of these bound states, I can just sort of cascade downward. So instead of going up from this ground state, I'm going to cascade down to this ground state. And instead of going from the n equals 3 to n equals 2 to n equals 1 state, I could just drop all the way down from the n equals 3 to n equals 1 state. Does anyone know what that transition is called? No, Balmer is when you wind up in the second state. Close. Lyman, it's a Lyman series. Lyman beta, yeah. So, very good. So that's at like 1025 angstroms or something like that. Fluorescence is the reason why we see planetary nebulae as beautiful as we do, because the hydrogen that's being expelled by this star at the end state of its life, leaving behind a very hot white dwarf, is being hit by lots of ultraviolet radiation. It's ionized in the center, which is actually why things become a little bit transparent, and you can actually see material behind it very easily, because it's ionized gas now. But then at some sort of critical radius here that depends upon the output of the photons and the densities and things like that, which we'll talk about next week, you wind up not having ionized gas, but you have very excited state gas. That excited state gas is able to fall back down fairly regularly, and this is the origin of this different color. These are actually lines, line emission, and mostly Balmer line emission. But this is the origin of these very beautiful planetary nebulae colors, fluorescence. So this is emission from a very sort of specific state of hydrogen, in the sense that it has to have a source of high energy photons around it. There's another process called Bremsstrahlung, and this is German for breaking radiation. Not break as in like rip apart, but break as in stop. And this is where I have a proton, and I have an electron which is moving near this proton. And this is unbound, so it's going to keep on going. But instead of just going off in a straight line, there's a Coulomb interaction between this electron and the proton. And what happens to the electron? If it's captured, then it goes to a bound state. That's called recombination. But if it's not captured, it remains unbound, then what? Somebody act it out. Yeah, like that. Okay, good. So the electron is deflected away from its otherwise straight line path. Does the proton move much? No, it's much heavier, right? What happens when I accelerate an electron? You radiate. What do you radiate? Gravity waves? Actually, a little bit, but no. You radiate a photon. The energy of that photon has to be more or less than the 1/2 mv squared of this electron. Correct. So if I have this sort of characteristic velocity, which is going to be a characteristic temperature associated with these electrons in an ionized medium, so this is where I have an H2 region. As long as this criteria is satisfied, I can wind up emitting lots of photons. And this is what's called Bremsstrahlin radiation. And if I want to put it now in terms of wavelength, this is lambda Bremsstrahlin has to be greater than something like hc divided by kt. This is 0.1 millimeters, t to the 10 to the minus 4 to the minus 1. Instead of calling this 1/2 mv squared, I could just call this kt. So at temperatures of 10 to the 4 Kelvin, I get infrared and radio emission. At 10 to the 6 Kelvin, I can get X-ray emission. There is what's called hot coronal gas that's all around us. It actually makes up about 50% of the volume of the Milky Way. It's very hot but very low density gas that actually can emit at X-ray wave bands because of this Bremsstrahlin emission. So I'll give you the classic picture of the different states of gas in the interstellar medium. This is the classical picture. Make a little table here of temperature in units of Kelvin, number density, little n, in units of centimeter cubed, because that's how we're going to do it. And we have the so-called hot phase of the interstellar medium. And this is about 10 to the 6 Kelvin. This has about 1 particle per cubic centimeter. The warm phase, that's 10 to the 4. That's about 100 particles per cubic centimeter. And the cool phase, that's something like 10 to 100 Kelvin, and particle density of something like 10 to the 5. What's the pressure of one of these phases in units of T and N? Yeah. So N times T is an interesting quantity. This is somehow related to the pressure. 10 to the 6 times 1, I can do that. 10 to the 4 times 100. 10 to 100 times 10 to the 5, something like 10 to the 6 to 10 to the 7. The interstellar medium, as it turns out, is in rough pressure equilibrium. And it sort of has to be that way, right? If you had some ball of gas and it was not in pressure equilibrium with the surrounding gas around it, it would either wind up expanding or contracting until it was in that state. This is the modern view, at least what Wikipedia says. It's got to be right. It's actually not too bad. Of the fractional volume, the temperature, the density, and sort of what state hydrogen is in this very complicated soup. So there are multiple different types of regions. You can associate some of them with basically cold at the top, sort of warm, and hot down here, and they've sort of subgrouped them. It should be apparent, of course, that we're not talking about sort of spherical blobs that are either hot, warm, or cold, but there's sort of a continuum between all of these different things. And whether a gas blob is in a sort of very hot state or whether it's in a very cold state depends upon what its history was and what's around it, right? If you're in a molecular cloud region and all of a sudden you turn on a bunch of O stars because you've just formed a bunch of stars, then what was once a very cold region all of a sudden becomes a very hot and perhaps very ionized region, and then everything changes, right? So star formation isn't just you have this cold cloud, it winds up fragmenting somehow, you produce this distribution of masses of clouds. If you wind up fragmenting in a way such that you produce a very massive O star, that O star can put out lots of ultraviolet photons, ionize it, and then all of a sudden the rest of the cloud can cease to satisfy the Jeans criterion, and then you don't make star formation. So there's this concept of self-regulated star formation, which you can see directly from this idea of these heating and cooling sources within these clouds. We'll mention a little bit more about heating and cooling in just a moment, but what I want to show you is some nice depictions of the region around the sun, a very sort of snapshot picture you can see up there, now sort of looking down onto the plane of the Milky Way of these various different blobs around us. Basically, all this black stuff is some fairly dense and cold regions. And you can imagine that if you look through some of these dense and cold regions, if they're associated with dust, that we would actually see them to be, we'd actually see it to be sort of dark. That's why these things are called dark clouds. But the sun turns out to be near the center of a fairly hot region, a very hot bubble. And that's probably due to some sort of ancient supernovae that occurred around us, which had a tremendous amount of energy, ionized a lot, and actually swept out a lot of the cold material, leaving behind this sort of warm material. The galactic center is that way. If I look side on to this, so now looking edge on to the plane, you can see, here's the galactic center that way again. You can wind up seeing what's called the chimney of this hot gas sort of going off the plane, and the sun is sort of near the center of this. Here's a molecular cloud that's near us where there's actually some ongoing star formation. Let me end with just sort of a listing of the sources of heating and cooling, just to give you a sense of the dynamics of how these star-forming regions might actually wind up satisfying the Jeans criterion if they didn't otherwise. So we're interested in the heating and cooling processes in the interstellar medium. First, let's talk about cooling. You can imagine that if I have a ball of molecular gas and it's emitting, say, CO emission, and it's emitting actually from all the different molecules. If it's actually getting to us, then it's escaping that gas. So this is just what's called line cooling. The other dominant way of cooling gas, if I'm not emitting in specific lines, but I'm emitting sort of in a continuum. What's that? Yeah, thermal. And what's interesting is that line cooling and thermal cooling sort of play off against each other. And depending upon the densities and the temperatures, you get different amounts of cooling per unit volume. We'll see more of that later when we talk about galaxy formation. But these two things are basically the dominant ways in which clouds will wind up cooling. But they're also heated. There's obviously ultraviolet photons from nearby clouds. And they can, the dust grains in this cloud can wind up absorbing that and can wind up heating up. this does something if you wind up taking, say, molecular hydrogen and you wind up breaking it up into atomic hydrogen. This is what's called chemical heating. Only because the energy is going to go proportional to the total number of particles times kT. So I've just gone from one particle to two particles. So I've increased the sort of chemical potential of the material. And there's other things that you don't have to know about, but I thought I would just put down. Things called cosmic rays, which are high energy particles that are probably accelerated in the shocks of supernovae. They wind up escaping these shocks at very high speeds, and those cosmic rays can wind up hitting matter in the cloud of interest, and basically just pushing that matter and accelerating it to a high velocity. So, in addition to this, you can also get some other processes that do the heating, but these are sort of the dominant ways of doing heating and cooling, and this matters for the creation of stars. Yes. Sure, yeah, that's fine. Let's do that. It's not very efficient because you'd have to get two hydrogen atoms in a very reasonably tenuous medium to actually decide to touch each other and decide to stay bound. And they'd have to give up a little bit of energy to do that. And yes, they could wind up chemically cooling, but it's not as efficient as these other processes in terms of the volumetric cooling rate. All right, so I think what we'll do is end with that. And what we'll pick up with on Tuesday is a derivation of so-called Strömgren sphere, which gives us a sense of the overall size of an H2 region around a hot star. There you have to balance recombination, so ionized material recombining into atomic material, with the ionizing rate of this that comes from the ultraviolet photons of the stars. And then we'll start getting more into the structure of the Milky Way.